Wait a minute. We've already covered steam turbines in Chapter 6, haven't we? Well, yes, we have. And so you're going to be analyzing steam turbines as part of Rankine cycle analysis. And it's my hope that you're going to be able to leverage what you've already mastered from Chapter 6 and repeat that um, in the Chapter 8 analysis of your turbine. And so this video says under Chapter 8, Steam Power Plant, Steam Turbine Basics. And so in some ways it might be a review, but there are complexities associated with analyzing a steam turbine. And now all of a sudden, it's more than just a homework problem on a steam turbine. It's kind of like 1/4 of a larger problem, a fourth or a fifth of a larger problem, because you've got boiler, turbine, condenser, pump, thermal efficiency to worry about. And so let's review the fundamentals associated with analyzing a steam turbine. And so, of course, when you're faced with your Rankine cycle analysis, there it is, process 1 to 2, the steam turbine process. On the TS diagram for the Rankine cycle, and I've shown the turbine with some irreversibilities associated with it. So it's beyond the ideal. It's the actual turbine. So remember, the reversible adiabatic steam turbine for the ideal Rankine cycle goes 1 to 2I, isentropic. But if we've got irreversibilities in the steam turbine, it's still adiabatic, but it's irreversible, 1 to 2A. And here's the sketch from a previous video. It's an old school steam turbine. It's still a great cutaway view of where we're going into the steam turbine through our throttling valve. In this case, we're taking a little extraction steam out of it. Let's not worry about that now. And then continuing to expand through the turbine blades, steam turbine blades, all connected to the same shaft going to a generator. And then off the steam turbine exit going off to the condenser. Another picture of an old school back pressure steam turbine. Well, what would your sketch look like? Okay, so nice pictures, all that stuff. What does your sketch look like on a homework problem? This had better look familiar, right? So the way to depict an insulated turbine is this trapezoid, because you're expanding the steam. So don't just draw a rectangle. That's for newcomers. Okay, nice a nice trapezoid showing the expanding steam. I'm not showing Q dot, am I? That's because the turbine is fully insulated. So on this sketch, I'm not showing Q dot in at all. I am showing W dot out. Turbine is producing power going in at state 1 and out at state 2. Okay. Oh, I do see. And what are our underlying fundamentals? Open system, steady state, steady flow. Since it's steady state, steady flow, one inlet, one outlet, M dot 1 equals M dot 2, and we'll just call that M dot. No changes in kinetic and potential energy. We'll just write that down, okay? One inlet, one outlet, just said that. And Q dot N equals 0, because our model for the Rankine cycle is going to be a fully insulated steam turbine. That's critical to write that down. Q dot N for this turbine, 0. So let's talk about the first law and second law combined for our steam turbine analysis. Here's our sketch. Looks like I've got a little sliver of a dot. Maybe I've got something over top of that, but thank goodness I see a little sliver of a dot, W dot out, coming in at state 1, out at state 2. The first thing we need to do is we need to analyze the isentropic turbine first. Even though we know we have an irreversible turbine, we're going to analyze the isentropic turbine first. So let's see, what's the fundamental there? For isentropic, S2I equals S1, constant entropy. So our job is to find H2I, okay? We know the pressure. Typically for the Rankine cycle, we always know the pressure, P2. And then if we know S2, that gives us two independent intensive properties, two independent properties. That enables us to find H2 isentropic. All right, here's a tip over here. S2I is usually a saturated mixture. Okay, usually for power plants, S2 isentropic is a saturated mixture. So you're going to go to your pressure table, look up S sub G and S sub F, and observe that S2I is in between those two numbers. And if it is, you're going to find X2 isentropic, the quality at state 2 isentropic. And then once you found the quality, you're going to write down H sub G and H sub F at P2 and find H2 isentropic. Ooh, that was a lot of work, and you weren't even asked to find H2 isentropic. Okay, well, why was that? Well, the why is that that's what enables you to find W dot isentropic. So look at this fundamental. Now that I've struck out Q dot N, you can solve for W dot isentropic if you know M dot, because H1 you've already got from the boiler study. Okay. It's common to not have M dot. And so your textbook works an awful lot in little w for a turbine, kilojoules per kilogram or BTUs per pound. Do you see it? That's just W dot over M dot. And so you can solve for little w isentropic, and that turns out to be, because of my pesky minus sign, H1 minus H2I. That's why you solve for H2I first. So you've got W isentropic. Now we're going to go to our second law of fundamentals. Turbine efficiency is generally a given number, and so that enables you to solve for W actual, since you just found W isentropic. Okay, I've got W actual. That's good. That's going to help for net work. Okay, W net. Okay, and so the first law for the actual process is going to be H1 minus H2 actual, similar to up here. Okay, so you see the similarity here. W isentropic is H1 minus H2 isentropic. So similar first law, striking out little q. W actual is H1 minus H2A. And so then you solve for H2 actual. You say, well, why should I do that? I'm not required to do that. It's common that you need to analyze the condenser. You may need to analyze the condenser. When you're asked to analyze the condenser process, you must have H2A, so you solve for it using this fundamental. W actual is H1 minus H2A when you're asked to perform the condenser analysis. Sometimes you need to, sometimes you don't have to. It all depends on the type of information you're given and what you're assigned to find. Okay. Well, those are the fundamentals for the turbine. Now, let me go back a little bit. The devil is in the details. Boy, I just breezed through that, didn't I? I just made it sound so easy. Gosh, you do this. Got it? Okay. The devil is in the details. And so I don't want to sugarcoat this, that it takes some hard work to get through this analysis, especially the first time. It's easier the second time. It's child's play when you do it 100 times. So you're going to be somewhere in between, but don't fall into that pitfall of saying, I saw the video, I see how to do it. I'm not going to work on any of the homeworks. I'll get this right in the quiz or the test. That would be a big mistake. So at least go through this twice before you get into your quiz or test. Okay, and so in my problem 816 that you can find in my playlist HW Solutions, I work through the nitty-gritty details, and I believe it's an English system problem for all four components, and particularly the steam turbine. Okay, I hope that helps you to see that Chapter 8 is more than a long list of formulas. It is really kind of a continuation of the material you covered in chapters 1 through 6. And the Rankine cycle is an applications chapter in which you're applying all of that work into a very important and powerful mechanical engineering system.